And yeah, tell all your friends about this in the adjacent spaces. Also, I guess before we get to Jimmy's talk, Jimmy Torre, who is our FUTO fellow this summer, and this is going to be hardcore nerdery. I hope you really enjoyed it. I think we have an announcement real quick that I would, yeah, so come up here and.
Hey everyone, just wanted to invite all of you to our hackathon this weekend. We have a hackathon every weekend, and the theme this weekend is breaking Bitcoin. We have a client, they forgot their password to their wallet, but they have the wallet. So if you have any background in brute forcing or anything of that nature, please come hang out with us this weekend. There is a reward for getting into the wallet and recovering the funds. Yeah. Just come see me after the talk, and I'll give you the information. We're on the east side of Austin. If you're familiar with Indra's, a warehouse, that's the location where our headquarters is at.
All right, good afternoon, everyone. So thank you, Razib, for the introduction. I'm Jimmy Torre. This summer, I was very happy to be part of FUTO as one of their fellows. So FUTO runs a fellowship program in which they seem to support a wide variety of projects, both within and outside of their usual remit, because this one is rather outside of their usual remit. I'll be giving this talk on a computational lens on self-justifying axiom systems, also SJAS. So, what did I apply with? My proposal to FUTO in part was to, within a host language, build a computational counterpart, an executable variant of a particular logical theory called SJAS. This logical theory exists in a number of papers published by Dan Willard over the course of the last 30 years, but all solo published. He was the only author. He had no grad students, at least no grad students who wrote in this vein, and there are limited citations in the literature which build upon SJAS. So interrogating what I find to be some very interesting properties of this logical theory is difficult and would be improved by having something concrete, something you can actually manipulate to investigate whether it does what it claims to do, as we'll discuss later in the talk. To that end, I've worked on a Tableau-style theorem prover for closed formulae of one particular SJAS, which is a family of theories called IS lambda A, or ISLA. And there's going to be some jargon front-loaded in this talk, and I'll try to break down that jargon. Also happy to take any questions throughout it. Raise your hand and I'll call on you if something doesn't make sense and that's stopping you from understanding what I'm saying. So ISLA is a weak first-order theory arithmetic with a semantic tableau deduction method, and this is primarily based off of Willard's 2001 paper. You'll note, curiously, that he calls it a self-verifying axiom system as opposed to a self-justifying axiom system, and that reflects that this is somewhat earlier in the lineage. It does, the original 93 paper calls it self-verifying theory, actually. And it becomes a self-verifying axiom system, and then it becomes a self-justifying axiom system, and somewhere along the way it's also called a introspectively aware or something like that, introspectively sensitive axiom system. This is very much the passion project of one professor at SUNY Albany. After he got tenure, this is basically all he worked on. So, when I say it's a weak theory of arithmetic, we're generally familiar with arithmetic in the informal sense, the schoolboy sense. We think of numbers as being natural numbers, negative numbers, fractions, so on and so forth. We have various operations that we can apply to them. And we don't particularly concern ourselves with the limitations of the number system itself, of the arithmetic system itself. We're concerned more with the limitations of what we can do with the arithmetic system. So if we are trying to solve a problem, solving the problem is what's of interest to us, as opposed to what arithmetic system are we using. And we can choose a variety of arithmetic systems. But the particular one here imposes certain constraints. That is the sub-additive constraint. We have integer subtraction, integer division, maximum, return x or y, whichever one's larger, the length of x in bits in its binary representation, the truncated root of x to the y-th root, and count. So a count of the number of ones in the rightmost j bits of x. All of these operations are sub-additive because the output can be no larger than the largest input. So obviously, if we're subtracting something, then the result of subtraction can be no larger than either the two inputs to subtraction. Same with division, same with maximum, length, so on and so forth. And then we have here this interesting definition of multiplication. This is not multiplication as a function, but rather multiplication as a relation, which defines itself on top. If we look down through all of the various constraints as to what x, y, and z can and cannot be equal to, we see that we're defining z divided by x equals y, using our integer division. So the crux of this is that we're limiting our arithmetic system to only being able to take input numbers and make them smaller. And this serves as the background language for the ISLA theory. There are some additional parts which I'll run over here. It is not critical to understand the group 1 and the group 2 axioms, but group 3 is fairly important. Insofar as understanding the group 3, it's a statement of consistency. So, if we have a theory of arithmetic, then using results going back to Goedel in the 1930s, we can encode logical statements as arithmetic statements. The particular Kleene fixed point encoding is very involved, but what it allows us to do is to say that there is no number, which is the no number y, which encodes the proof of 0 equals 1. So there is not a semantic tableau proof of the statement 0 equals 1. And this, we call this a consistency statement because if we were able to prove that if we were able to prove that 0 could equal 1, then our system would clearly be inconsistent. Right? That's a false statement. If I can construct the false statement 0 equals 1, it's going to contradict the true statement that 0 does not equal 1, and this will introduce an inconsistency into my theory. So between a weak first order theory of arithmetic that's based off of this language with these additional axioms defined in terms of that arithmetic, we then add the tableau deduction method. And now folks have probably seen proofs at some point in time, whether it's in analysis or calculus or geometry or where have you. Here, we're very concerned with not merely what are we proving, but how are we proving it? That is to say, what is the shape of the proof that is constructed? What is the particular thing which is actually a proof? A proof is supposed to be a demonstration that we're confident that a result follows from certain premises. But in the usual application of proofs, however we achieve that confidence is sufficient. If I demonstrate it via a very short proof versus a very long proof, doesn't matter. We're concerned with, have I demonstrated it? Here, we're again restricting ourselves, not to what are we doing, but how are we doing it? And in particular, we're employing a tableau deduction method. And a tableau deduction method looks like what you see over there on the left. We're going to take a formula, and this gives an example of a formula that's definable in ISLA. We negate that formula, and we decompose it. We look at its subcomponents, we perform transformations on them according to our deduction rules, producing a tree of statements, and at the leaves of each tree, if we can derive a contradiction, then we can show that the negation of our original formula is not allowable, which then implies that the original formula is allowable, and this then constitutes a proof of the original formula. Semantic tableau is very well established. It goes back to at least Raymond Smullyan in the 60s, actually earlier, to Beth is his last name, in the 50s, I believe. And it's really just a way of laying out the sequence of deductions that one performs. Usually, this doesn't matter. As an aside, we'll note that there's no modus ponens rule allowed in this, which basically means that we can't jump. We cannot jump from having A to having B using the inference A implies B. If we're going to have A implies B, we have to convert that into its normal form, which is not A or B, and then prove both sides. We call then our tableau deduction method fully analytic, because everything that you have to work with is present from the very beginning. Whereas with modus ponens, you can kind of hide internal steps. Okay, so part of this talk is telling you what I've done. The rest of the talk is going to be, why is it interesting? And this starts to get into why is it interesting. So if you accept the preceding constraints, of a weak arithmetic, of a particular form of proofs, then we can prove and be confident in the proof of the self-justification property for our self-justifying axiom system. And self-justification has two parts. One, that the system or the theory is consistent relative to an assumed consistent theory, which is parameterizable. In Willard's papers, it's usually with respect to Peano arithmetic, which has a number of evidences in favor of it being consistent. Like, this is where you sort of inject a human sensibility to it, in a similar sense to you inject confidence into a crypto system, or you inject security into a crypto system by having a seed which you are confident is properly random. Here, we're injecting consistency into our theory by measuring its consistency relative to an external theory. But then further, once we have this external theory and we've proven ourselves consistent relative to it, we have that group 3 axiom, which encodes a notion of consistency. And we can, in fact, assert that notion of consistency and not have it be countermanded, no matter what other operations or what other results the theorem proves. Prima facie, this is in violation of Gödel's second completeness theorem, which is a major limitative result, again from the 1930s. But SJAS is able to narrowly avoid it by accepting the particular restrictions which we've enumerated in the foregoing slides. Okay, so raise your hands. Who has heard of Gödel's second completeness theorem? Okay, we actually have a few. Okay, the point here, okay, then I'll review what it means, the second completeness theorem contra self-justification. So usually it's the case that if you're able to form, that is, say, if a theory is able to form a statement of its own consistency, that is, say, if it's expressive enough to be able to encode something like, for all y, there is not a semantic tableau proof of 0 equals 1 that has the Gödel encoding of y. If a statement can assert that at all, then it is in fact inconsistent. There will be some derivation which is possible within the system which contradicts this statement. There are some additional parameters and peculiarities, this isn't it, which we'll get to later, and those parameters and peculiarities offer the possibility of a loophole, which is what SJAS kind of wriggles its way through. But this is normally a very strong limitation on what systems can say about themselves. Now, oftentimes, we're not terribly concerned with what systems can say about themselves. We're concerned with what systems can say about other things. We use tools to refer to other things, to manipulate other things, to measure other things. It's relatively rare that we have tools which can self-reference. Except in software, where metaprogramming and transpilation and various other kinds of self-reference are ubiquitous, and which we utilize continuously. It's a very standard thing to compile a program. It's a very standard thing to have a bootstrapped compiler. It's a very standard thing to have a series of interpretations between a high-level language to a low-level language. And then at the high-level language, you're analyzing the low-level language again. Various operations in software development are self-referential. So the goal of this research, and partially achieved over the course of the summer, is to translate what it means for self-justification in a mathematical context to a computational context, which I assert can improve our confidence in the correctness of software, and confidence in correctness contributes to FUTO's goals of leveling the playing field, of biasing the use and development of software in favor of the individual contra conglomerates, contra oligarchs, contra the megacorps. Because it's one thing to say, okay, it's one thing to say, I trust that this software does X, Y, and Z. And if you trust it, fine. You don't need to go any further. If you say, I don't trust that software does X, Y, and Z, well, if it's closed source, you're out of luck. If it's open source, then the developers can say, oh, just audit it. Look at it yourself. And this works up until the point when it's a 30 million line code base, or you're not familiar with it, or you don't have time, so on and so forth. So there are various ways that we achieve confidence in correctness in software. And as your ability to demonstrate confidence in correctness in software increases, then your capabilities with respect to software producers increases. To give a couple of grounding analogies for this kind of relative process of referring to, progressively more and more precise notions of correctness. NTP clock strata. You begin with looking around, counting the seconds via your breath or via your heartbeat or just your internal circadian rhythm. You say, yeah, okay, that took about 10 seconds. And if that's all that you need, then good, you're done. If you need a little bit more precision, you can use the clock which is local to you on your computer or on your watch. If you need to check that that clock is correct, you refer to a local time server of some sort, and its job is to inform your mobile machine of what the time is. The local server refers to the time server, whose only job is to distribute what the time is. And the time server refers to atomic clocks, and the atomic clocks ultimately refer to the oscillation frequency of a cesium-133 atom. And so we ground out this process in some physical phenomenon. We have the same kind of measurement accuracy in flatness, smoothness. You're putting together a cabinet, and you say it's roughly level. If you need a greater assurance, you put a bubble level on it, you put a ruler on it. If you think that your ruler might not be good enough because you actually need some variety of precision, you can use a straight edge. That straight edge has various degrees of precision that it can be calibrated all the way down to tens or hundreds of thousands of an inch. Those came from the factory, and in the factory they were calibrated against a surface plate of some sort. And that surface plate was a piece of slate or granite or some other physical material whose roughness, whose surface deformation, is limited by the peaks and valleys of the molecular lattice that makes it up. And again, we ground out this relative deferral of guarantors in some physical phenomenon. And as we said, software correctness, you can, if you understand a piece of code, if it's written in FUBs and you can keep the entire compile chain in your head, great. And if that doesn't work, you can inspect the source code, interrogate it, say, oh, does this actually do what I think it does, run simulations in your brain. If that doesn't work, maybe you go to some sort of compiler, and hopefully that compiler has been verified in some way so that there isn't a compiler bug. If it is verified, it probably used some variety of proof kernel from the existing software verification tools out there. And that proof kernel was ultimately rooted in a mathematical theory of some sort. And this mathematical theory takes the role of our physical backstop for correctness. But note that software is reflective, and this process is recurrent. And once I have a piece of source code that does something, the thing which it might do is implement a mathematical theory. It might be a theorem prover itself. And so now you've got a mathematical theory that forms a proof kernel that guarantees that some piece of software corresponds to that mathematical theory, and infinitum, 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 going all the way down. So we have this term, externally audited proof kernel. Well, a human auditor, before he can make any statement about the proof kernel himself, or the proof kernel itself, has to say, I will not introduce consistencies. Or they have to at least have some confidence that they won't introduce consistencies. If you have a reviewer and the reviewer knows that they will introduce consistencies, then this is not a particularly apt auditor for your proof kernel. But we accept or reject a human audit off of basically informal methods. And the human says, I've got a PhD from Carnegie Mellon in functional programming, or they've got a good body of work in the past, or you have confidence in them for whatever reason. Trust is a rather opaque transition. You can simply impute trust in a person. But machines, being formal systems, do not operate, and in fact are moreover are obliged not to operate according to informal methods. If a machine says, I will not introduce consistencies, that is to say, if a mathematical theory implemented in some piece of software asserts that it is itself consistent, and so then whatever modifications it makes to the proof kernel, it itself will not introduce consistencies into that proof kernel. Normally, the mere fact of being able to state such a thing is forbidden by Gödel's second incompleteness theorem. And so to have an end-to-end software verification chain, a machine auditor which can make the inference, because I am not inconsistent, then I can make consistency evaluations of some subsequent theory is necessary. Okay. So with that as our motivation for what I've been working on, we'll go into a little bit more detail about SJAS, why it's interesting that it has these particular properties, why most things do not have this particular property of self-justification. And the ultimate underlying reason is that most theories of useful expressivity are subject to Gödel's second incompleteness theorem, which states that any logical theory which is sufficiently expressive, effective, and consistent is unable to effectively demonstrate its own consistency. And each number here is a parameter, a portion of the overall statement of G2, which, as we'll find, can be modified. These parameters can have different values, and we can tweak these values, and this will then shift us into a regime of formal systems to which G2 applies, and a regime of formal systems to which G2 does not apply. Trivially, if you had a very, very inexpressive formal system that couldn't express a statement of its own consistency, G2 is going to only apply vacuously. Right? This is an uninteresting system. We're concerned with statements that are, or theories that are actually consistent and sufficiently expressive, such that normally G2 would apply, but due to careful calibration of the arithmetic expressivity and the deductive expressivity, it does not. Yes, okay, so usually your only notion of expressivity is arithmetic expressivity. That is to say, what can you do? If you have Robinson arithmetic, you can only use addition. If you have Skolem arithmetic, you can only use multiplication. If you have Q or piano arithmetic, then you can have both addition and multiplication. And with piano arithmetic, you can have addition, multiplication, and you can also have induction, general induction. And there are more and more and more powerful arithmetics over to the right. And under the guise of Gödel's incompleteness theorem, this is what expressivity looks like. But with SJAS, the family of theories under the SJAS umbrella tweak two aspects of expressivity. What operations are allowable in the arithmetic, and what deduction methods are allowable. So we saw in the previous slides that the SJAS under consideration here has multiplication as a relational operator. There are other variants which have addition as relational operator, which have successor, addition of one as relational operator, or which have done it all, and you have to use very convoluted methods to even move from 0 to 1 and from 1 to 2. You can't simply say, and we'll add 1, and we'll add 1, and we'll add 1. Deduction methods can either be the tree style, the tableau method, which we saw earlier, or linear, Hilbert style. And again, with the tree, we saw that it's the shape of the proof. The deduction method defines the shape of the proof. A linear style deduction method is exactly what it sounds like. It lays out the sequence of consequences, one after the other, after the other, after the other. It does not require the decomposition into subordinate components that you have in the tree style. And using deductive expressivity, which here I'm calling deductive efficiency, and arithmetic efficiency, or expressivity, we find that that previous unidimensional division of the space of formal systems, in fact, is at least a two-dimensional division of the space of formal systems, and that there's some band in which trading off between particular combinations of deductive efficiency and arithmetic efficiency, you have the self-justifying property. Beyond that, G2 applies. Beneath that, you don't have systems which are capable of expressing their own consistency. They're not introspective. They can't engage in the kind of reflective behaviors which we're interested in for software verification. All right, now note I've changed here from talking about arithmetic expressivity to efficiency and also deductive efficiency. And I say this is not what's expressed in any of Willard's papers, but I say this to emphasize that what we're concerned with here is what can we say per symbol that we write down. If I give you multiplication, and I say you can multiply any two numbers together, how fast can you build a number? Well, you can build a number very quickly. I can give you 2 and 3, and you can build 6. I can give you 1 trillion and 17,000, and you can build 17 quadrillion. If I only give you addition, then in order to get to a similarly sized number, you're going to have to engage in more operations. If I only give you successor, then you have to engage in a linear number of operations with respect to the size of the number you want to construct. If I give you this curiously relationalized multiplication, you can't use this multiplication operator to build numbers any faster than however it is you produced your product in the first place. So if I have a system in which I've got successor, and that's a function, and I have multiplication, and that's a relation, then I could say that, yes, 2 times 3 equals 6. But for me to be able to say that, I have to provide 6, which then implies I already have 2 and 3, to my multiplication operator, which then constrains me to have built my numbers slower than if multiplication were a function symbol available to me. And so this is what I mean by arithmetic efficiency. How fast can you build numbers using the symbols which are available to you as almost a rate, the size of the number per symbol employed. Similarly, if we're talking about deductive efficiency, well, if I lay out a proof as a tree versus laying out a proof as a linear sequence, the proof tree will have more nodes. It will have more nodes in its AST, as it were, than the list of the linear proof. And to produce the same result, to produce the same proof of a statement, the proof tree will require more symbols than the linear proof. And so then here again, we have a notion of efficiency. How quickly can I produce a statement per symbol employed? But this is not the limit. There are more parameters which are discussed in Willard's papers. So we had one notion of consistency, and that was the semantic proof consistency of 0 equals 1. Okay, well, there are stronger notions of consistency that say, not only can I not produce 0 equals 1, but I also cannot produce any number of contradictory statements. It could be a fixed list of contradictory statements. It could be closing over all contradictory statements. And this then is a stronger consistency statement, which I may or may not be able to back up, depending on where my trade-offs are elsewhere in my theory, either in the language side or the deduction side. So this table over here, we have the self-justification level, and these are in reference to varieties of consistency statements. In particular, the ISLA system, which I worked with over the summer, is here, semantic tableau, type A, with a level 1 consistency statement. There are various other alternatives that we can imagine introducing that Willard does not address. We could imagine alternative group 2 predicates, and I'll jump back and talk about group 2 predicates. We can consider deduction methods that frankly weren't around in the 1990s, like Georgi Japarudz's cirquent calculus, which are designed to produce small proofs, but also still have a tree-like structure. So what's the actual bound? Can you have, how far towards linearity can you go before you have to start making trade-offs in your arithmetic system? And introducing additional parameters then suggests that as opposed to the unidimensional division of the space of formal systems, or the two-dimensional division of the space of formal systems, we actually have a very complex and not fully mapped boundary between where G2 applies and where it doesn't, and where self-justification applies and where it doesn't, and that this space of formal systems extends into a multidimensional space. So the research that FUTO supported over the course of this summer was in service to better characterizing this boundary and characterizing it in a way that becomes more concrete, interrogable, being able to think through what self-justification means, not just as symbols on a page in a mathematics paper, but as a theorem prover which has to actually store its intermediate representation somewhere, which has to actually crunch through the long and complex specification of the group 3 axiom. All of this required deep reading, looking at existing semantic tableau and other theorem-proving methods in the literature, and would not, I think, have been possible without the opportunity to sit back and deeply investigate one type of system within this broader family as part of a larger research project that ideally will come back around, improve self-verification tools, software verification tools, and in turn enhance FUTO's goals of leveling the playing field between the individual and the tech oligarchs. Separate to that main, to the main line of the proposal, there's also a whole bunch of other interesting research by Sergei Artemov, Lev Beklemyshev, Mihai Ganea, Niebergall, who's in Germany, and Pakamov, a student of art, who's a student of Beklemyshev. This is, SJAS itself is not terribly well known, but it sits within a non-trivial cluster of studies on G2, studies on Gödel's second completeness theorem. And as knowledge, as characterizations of SJAS are enriched, then I think that additional connections can be made to these various aspects in the local cluster. This covers the content of my talk. I'm going to go back and reference some things, ideally in response to questions. There's more information to be found on my Substack, where I've got the statement of my technical proposal. And then on my GitHub account, under the SJAS repo, you'll have basically all of these references and the code base for ISLA. I would like to make an official thank you and acknowledgement, a statement of support, that this theorem improvement related research was supported in part by the FUTO Fellows Summer 2025 program, in particular Aaron Wolf and Adam and Michael McConnell, all the folks who encouraged me to apply. Thank you very much. At this point in time, I'll take questions. Hopefully that the talk is not over. Thank you. Very good.
Test, test.
So you mentioned proving inconsistency with 0 equals 1, if you can prove that it's inconsistent. But you mentioned different strengths for this. I feel like most arithmetics I can think of, you can probably prove whatever you want given this. So can you give an example of a stronger inconsistency or what that means?
Yes. So the reason why notions of different consistency strengths is interesting, because Gödel's incompleteness theorems are a limitative result. If you can prove any inconsistency, then the entire house of cards falls down. But if you're trying to do the complement of that, if you're trying to show that a system is consistent and can prove its consistency, and all you've done is show that it can't prove that 0 equals 1, well, maybe that's the only contradiction it can't prove. Maybe there's 1 equals 2 that it could prove. So one extension to this would be to generalize both halves of that equality to show that equality itself, numerical equality, is consistent, which is to say that there is no pair of numbers x and y where x and y are distinct, that x equals y could be proved. And in fact, this generalizes pretty far. I believe generalizes to you can pick an arbitrary collection of pi1, which is it's the classification of particular kinds of arithmetic statements, arbitrary collection of pi1 arithmetic statements, and use that as your consistency, as your statement of consistency.
Thank you for the question. Are there any other questions?
we all questioned out? Oh, whoa, whoa, Thomas.
What do you have to chop off of arithmetic systems to be able to have this internal consistency property you're looking for?
So usually you can't chop off enough to have internal consistency. Usually it's the case that you run afoul of being sufficiently expressive to even express that you are consistent. Like this, this encoding of consistency is not feasible. You can't do this in Skolem arithmetic or Robinson arithmetic. And actually, it's not, it's Pressburg arithmetic. There's a typo in the slide. It's Pressburg arithmetic and Robinson's Q. My apologies, I'll correct that. Usually you can't actually make this statement at all. If you're capable of making the statement, then usually you are expressive enough such that G2 applies. What SJAS does is find a particular band of arithmetic expressivity, which is not just arithmetic expressivity, it's a trade-off between arithmetic and deductive expressivity, which allows you to assert the consistency statement while actually still being consistent without ever being able to contradict that consistency statement. So just to answer your question directly, I said this is Robinson, this should be Pressburger, my apologies. With Pressburg arithmetic, you only have addition. That is to say, you can make any statement you want about arithmetic so long as it's statements of addition. With Skolem arithmetic, any statement of addition that you want as long as it's statements about multiplication. In Robinson's Q, you have both addition and multiplication, and that is the usual dividing line. Once you have both, now you can express your own consistency, but you will run afoul of G2, and your expressivity will be too great. You'll be able to express both your consistency and a proof contradicting it. Whereas over on this side, you can't express your own consistency at all. So the interesting thing with SJAS is that it takes this otherwise infinitesimal dividing line and spreads it out, showing that there is some space in between the non-introspective and G2 applicable formal systems.
All right. Are there any other? Oh, you know what? I'll get back to you, Thomas, but let's get a new voice, fresh voice.
So motivating some of this research was, I think, the application to software verification. So what are some examples of the kind of verification? I'm primarily a security guy, and when I think of verification, I think of being able to, your point earlier about cryptography is that you cannot necessarily express with 100% confidence that some cryptographic primitive is perfect, but you give human level kind of trust-based cryptographic assurances, let's say. With something like this, how would this perhaps apply to security properties generally of programs, since that's often something someone might be concerned about when taking software from an individual versus a megacorp, let's say?
So I don't have cryptography up here on the analogies. However, it's quite germane because if I speak of a cryptographic strength, your cryptographic strength is proportionate to the purity of the randomness which you use to generate your cryptographic seed. And everything is in fact relative to that. A crypto system doesn't have an absolute strength, it has a relative strength. And the more that you investigate, how do you make things rigorous? The more that you find you never make anything absolutely rigorous. You make things correct with respect to something else. And you build up a network of relative references such that your overall confidence is improved. You inject the crypto strength, or you inject the strength into a crypto system via some very possibly physically derived random key string. And then you stretch it and you refer to it as your standard. So the particular applications of software verification are in fact this core loop. So the particular application which is motivating to me is the meta application of building systems which can plausibly modify themselves, extend themselves, act as independent self-auditors. At present, the best example of something which looks like a self-auditor is some variety of connectionist model, some variety of very non-symbolic. Still, or I should say, it's symbolic, but it's not, because it all boils down to matrix multiplication in the end. But it is not formal in the sense that we've established formally rigorous here, because it's effectively a black box. Like mechanistic interpretability of an LLM is an open question. The closest thing we have to active self-modifying software systems are not good old-fashioned symbolic AI, but some variety of autoprompter. If you can imagine a resurgence of formal symbolic rigor in that space, based off of strong formal guarantees of self-modification without self-undermining, then that would be the kind of software being verified that is motivating to me.
I got a question from the chat. Give me 1 second. And the question is from Anonymous, and they ask, how can SJAS serve as a foundation for AI systems that can reason about their own consistency, that can safely self-modify?
So if we imagine that we had a system which was consistent, but it was unable to assert that consistency of itself, then at best, any self-modification which it performs would have to be subject to this surrounding complex of external audit, which ultimately grounds out in a human sign-off. When I say that a hypothetical AI system engaged in secure self-modification could use SJAS, I mean self-modification in a rather strong sense, in an autarkic sense, A-U-T-A-R-K-I-C, one in which the role of the human auditor or the need for the human auditor is dramatically diminished or eliminated. Concretely, so as to move closer to that goal, one would want to implement a language of some sort atop of SJAS as its execution model, and then build a reasoning system within that language such that the reasoning system is linguistically constrained to have these same trade-offs of arithmetic versus deductive expressivity. And let's see if that answers Anand's question.
You mentioned ISLA a few times. I'm not sure what that is, and
Oh, yes.
maybe for like the talk itself. But.
We'll go to the top again. So the particular SJAS, so SJAS is a family of systems, and the particular system which I investigated, tried to investigate primarily, there was some branching out, was the IS lambda A theory, which refers to the introspective, IS stands for introspective system. Lambda is a parameter, a technical parameter, and A is referring to whatever the base system to which the SJAS is consistent relative to. So IS lambda A is just the name for a particular SJAS, and ISLA is the convenient way to refer to it.
Thank you. Do we have any other questions? Do we have any other questions? 1, 2, 3. Okay. I think we are complete. There.
So I'll be in Austin for 1 more week, and I'm on the Zulip, or FUTO Zulip. Do feel free to contact me via email or via my GitHub or via Zulip. Always happy to talk with folks about this topic, or in person. Thank you.
Yeah. Thank you again, Jimmy. Thank you for everybody who's here. There's still some time and there's still some food. So, hint. But next week, we're going to have a talk on AI and consciousness. So, I don't know. I hope you guys will be here with your conscious selves, you know.